How can we know how far a distant star is away from us? Why do streetlights get so much dimmer the further they are away? It all comes down to something known as the inverse square law. The inverse square law is vital for astronomy in determining astronomical distances by using something known as the standard candle. And it's also vital for understanding power in the solar system available. But first of all, we need to understand two important definitions. Firstly, luminosity. Effectively, it's the power radiated in watts. Now, this power spreads out like an expanding balloon, and we define the intensity. Effectively, it's the amount of power that hits a square meter at a distance d from the star or other stellar object. Now, to understand why this is so challenging, we first need to explore how distances are measured in the solar system. Now, rather than using kilometers or miles, we use something known as the astronomical unit. Now, 1 AU, or astronomical unit, is the average distance between the Earth and the Sun. I say average because it's not perfectly circular. Now, let's consider what happens as the Sun radiates energy in all directions. We describe the Sun as having a specific amount of power, or luminosity. So think of this 1 second's worth of energy spreading out like an inflating balloon in all directions. So now let's say if we double the radius of this energy per second balloon, do you notice it spreads out over 4 times the area, as you can see here? Now this leads us to a critical concept called the inverse square law. If you double the distance from the Sun, each square meter of space receives only 1/4, or 1/2 squared, of the original power. Now looking at this, let's break it down into astronomical units. So at 1 AU, the Earth's distance, you need 1 square meter of solar panel in orbit to capture a certain amount of energy. At 2 AU, you would need 4 square meters. At 3, you'd need 9 square meters where much of the asteroid belt is, and so on. By the time we reach Jupiter, which is just beyond 5 astronomical units, we need 27 square meters. Now here's a quick chart for reference. The furthest planet, 30 AU, you need over 900 square meters of solar panels. For Jupiter, it's about 27 square meters. This is still a considerable challenge. So look now as we zoom out to see the whole picture. So the intensity, or the watts per square meter, can be found by looking at the total power emitted, the luminosity, divided by the area of which it's now spread out over. So this would be L divided by 4 pi r squared, as the surface area of a sphere is 4 pi r squared. Another way of putting it, the intensity is inversely proportional to the distance squared.